Our next speaker is Adrian Lareida. He's a scientific assistant at the Institute of Machine Tools and Manufacturing at the ETH in Zurich. He's working on an industry project together with Glaston, Switzerland. And because he will have two presentations in a row, the first part of his presentation is investigation of braking stresses on cut-edge quality. Please, Adrian, the floor is yours.
Thank you. So hello, welcome everyone to my first presentation today. It's about the investigation of braking stresses on cut-edge quality. And this is part of a bigger project from InnoSwiss. It's like the Swiss Agency for Innovation Funding. And these projects always include an industrial partner. In this case, it was Glaston. And on the other side, there are the universities. In our case, in this project, we had the University of Applied Science, Ost, and we have, where I'm from, the IWF and their partner Inspire, together working on this project. Let me start with the agenda for this presentation. So I'm going to give everyone a brief introduction into the glass cutting process and why we did this project. And then I'm going to tell you about what experiments we did, what simulations we ran, and what were the results from that. And I will end with a summary and the outlook. So let's start with the glass cutting process. Here we see a line for the cutting. Here in this case, that's the cutting table where the glass is cut and broken. Then the next step would be the grinding. And here you see the control unit of the machine. And this is the drilling stations where the holes will be drilled into the glass. And afterwards, it's usually going to a washing machine for further processing. Usually on these machines, it's used in the automotive display and architectural glass processing. The usual glass thicknesses range from 0.5 millimeters to 8 millimeters. And the future trends on these machines will be thin glasses and specialty glasses, stronger glasses. And the most important parameters on these machines is the cycle time and the quality that is reached of the glass. So here we see on the cutting table a bit more detailed view. We have on the front, we have this braking sphere. It's a sphere embedded in the holder, and we have our cutting wheel. The cutting wheel in detail is quite a small part, and it is used to create a fissure in the glass surface. Basically, we want the middle crack down the glass to be able to break it afterwards. And due to the stresses introduced, we also get lateral cracks, but yeah, we can't really prevent this. But we want to maximize kind of the median crack and minimize the lateral. Then we have on the left, you see this blue conveyor belt, and below this, on this special type of machine, we have a rotating table, and this whole part can rotate. And we have the satellite, we call it, which can move inwards and outwards radially. And the braking works like this, so that the glass sheet is on the table, on this conveyor belt, and in the middle, like here, it's held down by a vacuum. And then the satellite pushes from the bottom side to the glass to support it, and on the outside the braking sphere presses from above. And the big advantage of this system is that you don't need to switch the the template between different shapes. So, and because of that system, we asked basically the question, could we use this possibility to like position the satellite independently, like not with a template, but we can move it? Can we influence the quality of the glass edge? And furthermore, what insights could we get from a finite element simulation of the breaking process? So we put down a list with parameters to investigate, and we focused first on the geometry. We had no auxiliary cut to support the glass that we cut, and we have two types of auxiliary cuts. I'll show them afterwards. And then we had the satellite position. We relatively positioned the satellite in a lead, in a parallel, or in a lag position to the breaking sphere. We used two different glass thicknesses of 2.1 and 2.85 millimeters. And we changed the height of the satellite to be 1 or 2 millimeter above the, like sticking out of the table. So to the geometry, here you see the geometry that we cut. We basically have two auxiliary cuts. One is just a 45-degree angle, and the other one is like a slightly angled cut. And the main part that we cut had quite a long section of 1 meter in length and then a 100 millimeter radius. And for lead, lag, and parallel, to imagine it a bit better, if we have on top here the path of the breaking sphere, then parallel would mean that it's really with a distance of 30 millimeters below the cut is the satellite. And a lead of 30 millimeters means just this distance is 30 millimeters ahead, and lag on the opposite. And then we run the experiments, and we use the high-speed camera to record the breaking process, and we triggered the camera together with the machine so that we knew exactly where the positions was of the axis together with the breaking sphere. And the reason for that was to look at where the crack is propagating and at which position the breaking sphere is relative to the position of the crack. And with the parts that we broke out of the glass, we put some small samples, one in the middle of the radius and one at the start of the radius. Basically that it's always in the vicinity of one of the auxiliary cuts. We broke them out and investigated the bottom side of the glass under a microscope. And here are some examples of the results. I show this because we had a system to like assign a certain quality to each of the experiments. And here on the right side, we see, for example, a bad underside, because it has very large irregular chippings. And then we had some specimens with a kind of acceptable quality because it was quite homogeneous and not that large of chippings. And then on the left we see what we actually want, like no chippings at all. And for the simulation side, we use the software Abacus, and we run dynamic explicit. We use the dynamic explicit solver to run the simulation of the breaking. And we used 4 experiments to compare. We used 2 good examples and 2 bad quality examples. And also we used for the cut, we used the mass scaling to lower the runtime of the simulation. And here we see the bulk part of the glass. It was we set it as elastic property with the kind of standard literature values for glass with the E module of 70 gigapascal, Poisson ratio of 0.22, and the density of 2,700 kilograms per cubic meter. And then we had the cut line. There we introduced the brittle cracking model. We used different failure stresses. I will show that in the results as well, because we weren't really sure about that. And we used also from literature a value for the mode 1 fracture energy of these 0.008 Newton per millimeter. And we put the whole thing on a support. We can see it a bit in the background here on the edges. That should mimic the table where the glass is laying upon. And we activate the gravity so that we can hold it down. And the vacuum was simulated by fixing some nodes in the middle of the glass. And then we also simulated the satellite and the sphere, and we took the paths directly from these 4 experiments so that we have exactly the same positions. And the satellite, it either moved, depending on the experiment, it either moved 1 or 2 millimeters into the glass. And the sphere, we used a constant force boundary to have also the 40 newtons, like in the experiments. So now let's look at the results. I tried to condense the experiments down to, it's basically 2 slides. Here we see the thin glass, the 2.1 millimeter glass. And on the left, there's the results for when the satellite is in its lower position, so meaning just 1 millimeter above. And here on the right, we see it when it's in the upper position. And then the quality is on the y-axis, and on the x, it's like the position of the satellite, if it's lagging, parallel, or leading. And also the different symbols symbolize the type of cut. So like the circle here is no auxiliary cut. Then the square is the first type of auxiliary cut, 45 degree, and the diamond is the second type. And we can see that we have quite an influence of these parameters on the quality. And we can also see that for the case of the 2.1 millimeter glass, we only achieve excellent quality with the second type of auxiliary cut. But depending on the height of the satellite, we have some flexibility that we can use leading or parallel if the satellite is down, or we can use only leading when the satellite is a bit higher up. We also see that the circles are in any case deliver bad quality, so no auxiliary cut is not possible to achieve a good quality. And with the other type of auxiliary cut, we can reach at least some kind of acceptable quality levels. And this changes basically pretty much when we look at the thicker glass. So the glass thickness has also quite an influence. Here for the thick glass, we only did use the auxiliary cuts. We did no experiments with no auxiliary cut. And we see that it's very depending on, for example, if the satellite is in its lower position, then lagging is quite good for the first auxiliary cut. When it's just 1 millimeter higher up, it's quite the opposite. It's suddenly bad. And so these parameters all change, and it's very difficult to see how are they really related to each other. Here we see the two different auxiliary cuts, and we used the high-speed imaging and the simulation, and compared where was the braking sphere, where was when the x-coordinate is horizontal, where was the braking sphere compared to the crack tip. And we looked at 2 points, so we waited until the crack tip was here and recorded the position of the braking sphere. And then the second point would be on the black dot, and we recorded where was the position of the braking sphere compared to the crack tip. And we can see that for experiments, these are solid lines, we have some kind of a positional difference between the movement of the crack tip. And with the simulation, we didn't have it for when we use, as you can see, a failure stress of 10 megapascal. In the case of a higher failure stress, we at least reached quite a good agreement for the blue experiment that we simulated. It's basically on the same angle, but we didn't achieve it for the green and the black experiment. Yeah, there could be like different reasons. It's quite a delicate topic to simulate this movement of the crack. There could be any kind of influence, and the crack is already on a quite different position. And here I can show you the simulations. On the left we have an example for a good quality cut, and on the right we have one for a bad quality cut. And I will play now the video, and you can maybe spot what's the difference between, like first the satellite goes up and then the braking sphere moves towards the glass, and now the sheet is basically broken open. And I don't know if you have noticed it, but quite in this region, when the satellite is here, it rips open, and it rips quite differently. And if we stop the time at this point, we see that for the bad quality, we have quite more like a higher mode, let's say, and a higher movement. So, and we assume that this could be the necessary energy that is causing this chipping on the bottom and causing the bad quality. So to summarize, first with the first graphs we saw that it's quite difficult to model the quality of the like to predict the quality based on what parameters are set, because they're quite interdependent. And we also can see that that the parameters are influential, all of them. And the satellite position, we can use it technically to optimize for a better quality. So we don't have to change any setting, but only by moving the satellite to a different position we can optimize the edge. And then based on the simulation, we first wanted to look really at the stresses, but because it's such a dynamic process, it was very difficult to get any information really from the stress field. But we at least gained some intuition about the crack opening. And we can use the simulations to try different positions of the satellite, try it out, look at the simulation results before going to the actual machine. And yeah, as I told on the last slide, like the opening is quite in a higher mode, and it's quite violently in the case of bad quality. And now for the last bit, the outlook, we can definitely try more for the modeling with extended experiments, with more parameters to get an insight, and to maybe also adapt the model really. We only used kind of response surface models, so we can also test different geometries to see, like to extend it, to test more. And the goal in the end would basically be a recipe. What should the user of the machine set depending on what type of geometry he has to cut? So what kind of auxiliary cuts he can use, what doesn't he need to use, lead, lag, parallel. And also we can standardize this simulation setup because it's quite similar. Like we have always this braking sphere and stuff. Only glass thickness can change and the geometry. And by standardizing this, we can give a tool for the user to to get more intuition. And with that, I'd like to thank you for your attention, and I'm open to any questions. Thank you.